So this is a presentation on identifying the rejection criteria for hypothesis testing. And here we go.
So this presentation is about rejection criteria. In the previous lecture, we talked about how in a story problem you can identify a null hypothesis and an alternative hypothesis. And then the idea is you would go out and collect data, use your data to try to decide whether or not to reject the null hypothesis. And you have to have a way of setting up the conditions ahead of time. What would be the rules or the criteria that you're planning to use to decide whether to reject the null hypothesis or not. This presentation is just, it's not about how you choose the rules, it's about just how different ways of expressing what the criterion is, the language for talking about it. So this is an example that we used in the previous lecture for identifying hypotheses. We have two hypotheses and some evidence here. The EPA believes that the population mean exhaust emissions of nitrous oxide for a particular car is 1.45 grams per mile. And they also believe that they know the standard deviation, and they believe that the emissions are normally distributed among all the cars of that model. So this is one hypothesis, and then the car manufacturer disagrees. They think their new process has reduced the mean level of exhaust emitted for this car model. So we have two different hypotheses about the population. The null hypothesis is this first one from the EPA. We can tell it's the null hypothesis because it's specific. That's an equal mark right there. They have just one particular number in mind for the mean and standard deviation. And it's the null hypothesis because they're going to just go on believing that until the car manufacturer produces some evidence to the contrary. So the burden of proof is going to be on the car manufacturer to show that something has changed and this mean and standard deviation are not correct anymore. So here's the alternative hypothesis bearing the burden of proof, but less specific. They're not saying mu is any one particular number. They have a whole range of possibilities. And so they go out and collect some data to try to resolve the issue. You get a simple random sample of 28 cars and get a sample mean of 1.21 grams per mile. Now, so the sample mean came out to be less than what the EPA thought for the population mean. So it makes us think we should just reject that 1.45 in favor of the alternative because, well, we got a sample and we saw less than 1.45. So is that the end of the story? Game over? No, 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 no. The EPA can say we just got lucky with our sample because there's 1 million cars out there and we just looked at 28 of them. So that's the complaint we have to address, is whether we could have just got so lucky. The EPA wants to know, how low is that 1.21 really? Is it significantly less than the 1.45 or not? The manufacturer wants to know, well, so how low would it have to go before you think it is significant? So that's two questions. How low is it really in a practical sense, and how low would be low enough to make us reject the 1.45 in favor of the idea that the population mean is really less than that? So how low is it really? Sure, it's 1.21 grams per mile. So what? Under the null hypothesis, would that be unusually low? Or would a lot of samples produce sample means that small, even if the 1.45 was really the truth? So it's like the question in an earlier homework, whether we needed to find out if Mabel the orangutan had a fever. We had her temperature was 88 degrees Fahrenheit. Is that a fever? We don't know, because we don't know how she stands relative to other orangutans. We need a measure of relative standing. So we have one measure of relative standing so far that we know about. It's the z-score. So if the null hypothesis was true, then how many STDs above or below the mean is this 1.21 grams per mile? So if the true mean was 1.45, then the sample mean that we got is 3.18 standard deviations below the mean. So now we know if the null hypothesis was true, then what we saw is pretty far below the mean. Just thinking about that 99.7% rule, you can tell we got something out there on the edge. Okay. So, what would be the probability of getting such a low sample mean, the 1.21 grams per mile, or equivalently the negative 3.18 STDs, same thing? What would be the probability of getting that if the null hypothesis were true? Have we seen something really that unusual? And it matters because the EPA will only be convinced to reject the null hypothesis, to reject that 1.45, if we can argue that our observation is really unexpected, would be rare if the null hypothesis was right. So we need to argue that we have seen something that would come up very rarely under the null hypothesis. And that might make us doubt the null hypothesis. So this probability of seeing such a low sample mean under the null hypothesis, that probability is called the p-value of the data. Can we calculate it? Sure. If statement 3 of the central limit theorem tells us that the sample mean here is normally distributed because we have a simple random sample and under the null hypothesis, X is normal. So we did not have a big sample, it's under 30, but we don't care because statement 3 of the central limit theorem says, well, but if X is normal, then X bar is normal. So we can calculate how often would such a small sample mean occur under the null hypothesis. And so we get the p-val. We're using the norm dist function because we have what we need to know that X bar is normal. You can do that calculation in Excel. You can either put in the grams per mile all the way across or the STDs all the way across, either way. So how low is our X bar 28 really? We've answered the question in 3 ways already. It's that many grams per mile, that's how low it is. It's that many STDs, that's how low it is. And it has this little p-value, 0.07%. That's how unusual it would be under the null hypothesis. All three of these are telling you just how far out near the tail of the null hypothesis distribution, how far out was our result. The question is it far out enough to convince the EPA to reject their hypothesis? I don't know. What does it take? Before we calculated any data, we should have reached an agreement about what it would take to convince them. Best if you can establish that up front. Don't want anyone to change the rules on you. But not just that, you want to know before you collect data, like you want to decide about your sample size and so forth, to make sure you can meet the criterion. So they have to tell us how low is low enough, and the answer to that question, how low is low enough, is called the rejection criterion. And it's whoever believes the null hypothesis, in this case the EPA, they have to choose the criterion, because only they can tell you what it would take to convince them. Okay. And when we did our p-value calculation, it had to be based on the null hypothesis. We have to be able to say to them, see, if we calculate probabilities your way, then what we just saw should not have happened. But it did, so you must be wrong. So you got to work within their worldview using their hypothesis to do your calculations, and then show the conflict between that and the data. So we had three ways to say how low is our sample mean. Similarly, they have three ways that they could express how low would be low enough to reject the null hypothesis. So, three ways they can express it. They can give you a critical value of the sample mean, where, okay, if you get fewer than this many grams per mile, we will reject our null hypothesis. Or they can give you a critical z-score. We say, okay, if your z-score, your green z-score, is below this red z-star, that's far out enough. Or they can give you a cutoff probability called the significance level. Where, okay, if your p-value is less than that, then that's far out enough. They can express it in any one of those ways, but it's just a difference of expression. It doesn't change whatever their cutoff is. And I'm going to illustrate and discuss each of those a little bit in the next couple of slides. So there's three ways to express the rejection criterion in a picture. Okay. So like I said, there's X star, X bar star, or Z star, or alpha. So in the picture, if they give you an X bar, a critical value of the sample mean, if they give you an X bar star over here, you're saying, all right, if your sample mean falls to the left of that, we'll reject. Okay. So they'll reject if your sample mean, the green one, with no star, falls below their critical value. Or if you took that and you converted it to a z-score, you know how you convert, you subtract the mean and divide by the standard deviation. If that comes down below the z-star, same thing, it's telling you where to reject. Or if it comes down so that the tail area out beyond the X bar is less than alpha, in other words, it comes down in here somewhere, then they'll reject the null hypothesis. Let's make the picture just a little more detailed for each of these. Let's just talk about the one with the natural units, the grams per mile. Okay. So their criterion for rejecting the null hypothesis is if the sample mean, X bar n, is less than the critical value of the sample mean. And it's using a less than because in your alternative hypothesis it was a less than. If it had been a greater than in the alternative, this would be a greater. Okay. So your factual evidence is your sample mean, and their cutoff for what makes a reasonable doubt is the critical value. It's just like a jury trial. You have to prove beyond a reasonable doubt. Somebody has to decide, so what's a reasonable doubt? The one with the star, the red one, that's the when standardized units, you'll reject their null hypothesis if the z-score from your data is less than the z-star that they set up as the criterion. So you get your data, you get your X bar in, and you convert it to a z-score using this formula, keeping the stuff that comes from data is green, and the stuff that is your criterion is red, and then the information from the null hypothesis is blue in the formula. So again, it's like a jury trial. Your evidence is Z, and how low does Z have to go to eliminate reasonable doubt? The criterion for reasonable doubt is the Z star. Or as a significance level, if the probability of getting such a small X bar is whatever you got, you get a sample mean X bar, and then you say, well, how likely was that under the null hypothesis? But how likely is that? That's your p-value. And if that's less than alpha, then your evidence has eliminated a reasonable doubt. Now, the idea of alpha is it's kind of like how much doubt is reasonable doubt. Okay. So the sample mean will almost always differ a little bit from the null hypothesis. The question is whether the difference is big enough to be significant. In a later lecture, we'll learn how to calculate these p-values, the probability amongst all possible sample means. How often would they go so far out as yours went? That's the p-value. And then if that p-value is less than alpha, you might convince the EPA to reject their null hypothesis. You should negotiate that alpha ahead of time. So I want to give you a picture of what the p-value is. So in this story, the rejection zone's on the left-hand end of the distribution because the alternative hypothesis had a less than in it. We're going to reject this 1.45 mu from the null hypothesis. The null hypothesis is that this is the distribution. They've told us the shape was normal. They told us the mean was 1.45. They gave us standard deviation. This curve is the null hypothesis, and we're going to reject it if we get a sample mean far enough far enough off to the left. Left because of the less than in the alternative hypothesis. So this, if the sample mean that you got was where this green one is over here, that would mean we would reject the null hypothesis. And so if that happens, what could we say about the p-value? I need to show you where's the p-value in this picture. So the p-value, it's the probability that you would get such a small sample mean. Like if the null hypothesis was true, then what's the probability we would be so far off to the left as we, in fact, were? And so you see the green area, the p-value here, is less than the red shaded area. That's alpha. And that happens, that the p-value is less than alpha happens when the sample mean falls in the rejection zone to the left of the critical value of the sample mean. Critical value is the red one with the star on it. Or if the z-score fell below the z-star. Just depending whether you want to talk in the grams per mile or the STD units. Okay. But now, it also might happen that your sample mean falls closer to the null hypothesis mean. So if it falls over here, sure, it's weak evidence against the null hypothesis. And you always get some degree of evidence against the null hypothesis because you're rarely going to hit it right on, maybe never. But it's weak evidence because before all of this got started, in this story, the EPA set up, well, here's the cutoff. Back here, these red alpha or X bar star or Z star, that's the cutoff. So if the sample mean falls too close to their hypothesis, they will not be convinced to reject their hypothesis. Okay, so what happens to the p-value when we don't reject the null hypothesis? Let's shade in the p-value over here. That's all of this. Practice the coloring skills from my youth. Okay. Well, anyhow, that's the green part's the p-value, and that green area is bigger than the red shaded area, so the p-value is more than alpha when we don't reject the null hypothesis. So the EPA, they don't have to tell you the X bar star or the Z star. If they just tell you the alpha, that's good enough. If you can calculate the p-value, then you just compare. If the p-value is less than alpha, you reject the null hypothesis. If it's more than alpha, you